Hi everybody, welcome back. This is Unit 7, Lesson 3, and we're on Section 3. I like it when it works out that way. We're talking about the gas laws, and we're going to talk about the relationship between pressure and volume, pressure and temperature and volume. So you can only compare two of the variables when the third is constant. So if we want to look at the relationship between pressure and volume, we must be at constant temperature. And basically this little picture over here shows you what you did in the lab, right? When the syringe is compressed or depressed, all those gas molecules are in a tiny space. There's low volume. This is the pressure gauge. So you can see the pressure gauge is past halfway. Down here, when you increase the volume, then you have that same number of gas molecules in now a larger space. And so they will hit the walls of their container less frequently. And you can see that made the pressure gauge go down. So you notice that pressure and volume do opposite things. When the volume's high, the pressure's low. When the volume's low, the pressure's high. This is what we call an inverse relationship. So at constant temperature, the higher the volume, the lower the pressure. They do opposite things. This is known as Boyle's law, as Robert Boyle was the scientist that discovered this, though you don't need to know that name. Okay, so this is an inverse relationship. As one goes up, the other goes down. As one goes down, the other goes up. Okay? This is the typical graph for a pressure-volume relationship. Notice that it never approaches zero. Okay? I mean, it never goes to zero. It may approach it, but it doesn't go to it. And I always like to draw labels on my curve. So this would be like low pressure. When the pressure's low, the volume is high. Okay, when the pressure's high down here, the volume is low. So that will help you get the idea of an inverse relationship. It's also important that I draw your attention to the idea that it is not this. Okay, it's not straight, it's curved. There's some mathematical term for that. Hyperbole, parabola, something. Parabola, something like that. But it should be, I'm just going to make it up, parabolic shaped, okay? It should be curvy, not a straight line, all right? It should be curvy, okay? They will give you the straight line as a choice. I just want to make sure you understand. When we talk about these relationships, again, it's important that you know what units pressure are. So atmospheres is a unit of pressure, or torr, or millimeters of mercury, or pascals, or kilopascals, or pounds per square inch. It will just help you recognize pressures when you're given them. The equation to represent Boyle's law is P1V1 equals P2V2. That is the relationship, or that is the equation for an inverse relationship, okay? Where V1, the ones are your initial conditions of your gas, and then you're going to do something to it. So these would be your final conditions of your gas, after you manipulated it, after you messed it up. Right then, the next one is Charles' law, and Charles investigates the relationship between T and V, which means our pressure is constant. We can only investigate the temperature relationship of a gas when the temperature is in Kelvin, okay? So this only holds true when the temperature is Kelvin. So what you can see from the curve is that as temperature increases, volume increases. The higher the temperature, the greater the volume. The higher the temperature, the higher the volume. These do the same thing. As one goes up, the other goes up. And notice this is a straight line. Okay? It is not curvy. It is not parabolic, if that is a word. So this is what we call a direct relationship. And again, remember the temperature has to be in Kelvin. They will give it to you in Celsius. The conversion for Celsius to Kelvin is that you add 273. So if you had 10 degrees Celsius, then your Kelvin temperature is 283 Kelvin. You just take 273 and add it to your Celsius temperature. When we are calculating with these, temperature always has to be in Kelvin. You can recognize volume units if you're given liters or milliliters or even cubic centimeters, centimeters cubed. This is commonly used in medicine. If you watch any of like House or any of those shows, they might say something like, give me 5 cc's of epi-stat. cc stands for a cubic centimeter. A cubic centimeter is the same as a milliliter. It just sounds way cooler to say, give me 5 cc's rather than give me 5 mLs, right? Just cc's roll off the tongue. The equation for volume and temperature is different than Boyle's law. It's V1 over T1 equals V2 over T2, okay? And again, remember, the temperature must be in Kelvin. That is super duper duper important, okay? The final law is, it's called Gay-Lussac's law, and he investigated the relationship between pressure and temperature. And in order to keep the volume constant, the higher the temperature, the greater the pressure. Right? If you heat a gas in a closed container, you can see here, here's the idea. This is at 75 Kelvin, and this is at 150 Kelvin, and this is at 300 Kelvin. And I know it's kind of hard to see, but the greater the temperature, the more energy the molecules have, so they hit the walls of their container more frequently and with more energy. And so they hit more frequently and they hit harder, and that's why the pressure here is 400 kilopascals, but the pressure here is only 200 and the pressure here is only 100. So you can see as you increase T, you increase P, right? It makes sense that the hotter it is, the greater the pressure will be. Again, this is a direct relationship. They do the same thing. So you'll get the same graph that you had with V and T with P and T. As pressure goes up, temperature goes up, and vice versa. The equation for Gay-Lussac's law is P1 over T1 equals P2 over T2. Okay? And that is the relationship between temperature and pressure. And again, remember, anytime we use temp, temp is in Kelvin. Anytime you plug that in, temp must be in Kelvin. And so it's kind of a pain to have to remember all three of these relationships, PV, VT, TP. So what we've done is we've combined them into one law called the combined gas law equation, right? And I'll just give you that equation and kind of show you how it works, and we'll be done for today. So this is in your reference tables, but really what we do is we put together all the laws of Boyle's and Charles. P1 V1 over T1 equals P2 V2 over T2. And again, temp is in Kelvin, okay? Now, that's great if P, T, and V are all in the equation, but here's what's amazing. What if temperature is constant? If anything is constant in this equation, you just remove it. So if they tell you temp is constant, look at, you just get rid of it in the equation, and now you've got Boyle's law, P and V, right? If they tell you, hold on, let me get that back. If they tell you pressure's constant, then you just remove pressure from the equation, and now you've got Charles' law. V1 over T1 equals V2 over T2. And finally, if they tell you volume's constant, then you remove volume from the equation, and now you have Gay-Lussac's law, right? You have his law with P1 over T1 equals P2 over T2. So something, you can get any three of the ones that we've already talked about simply by removing the constant from this equation. However, if nobody's constant, you got to leave them all in. P1 V1 over T1 equals P2 V2 over T2. So this equation's given to you in reference table T, and we'll be doing some practice with it throughout the course of the week. That's it for today, everybody. Have a great night, and we'll see you in class tomorrow. Bye-bye.